Electricity generation, question 2. A wind turbine has a blade length of 17.5 meters. Part A. Calculate the mass of air passing every second if the wind speed is 7 meters per second and the density of air is 1.3 kilograms per cubic meter. Well, from the datasheet we get that the mass of air will be equal to the density multiplied by the volume. And the volume in this case is given by the area swept out by the blades multiplied by the speed of the air multiplied by the time taken. The area swept out by the blades will be a circle of area pi times the radius of the circle, or the blade length, squared. So we get that the mass of air is equal to density multiplied by pi multiplied by the radius or blade length squared multiplied by the speed of the air and multiplied by the time. Density we're given here as 1.3 kilograms per cubic meter. The radius, I said, was the blade length of 17.5 meters. The speed of the air is given here at 7.0 meters per second, and we're given that this is for 1 second, so the time will be 1 second. Putting the numbers in gives us an answer of 8,755 kilograms. Part B. The turbine is 53% efficient. Calculate the amount of energy it will provide over a 24-hour period if the average wind speed is 7.0 meters per second. Well, for this we can work out the kinetic energy of the air that will pass through, and the kinetic energy is equal to half multiplied by the mass multiplied by the speed squared. In part A here we found the mass passing through in 1 second, and so putting that into the equation here we get half multiplied by the 8,755 kilograms per second multiplied by 60 to get the mass per minute, multiplied by 60 again to get the mass per hour. We have 24 hours and the speed of 7 meters per second squared, giving the kinetic energy of the air as 1.85 times 10 to the 10 joules. But we're told that the turbine is only 53% efficient, and output energy is equal to efficiency multiplied by input energy. This is a rearrangement of the equation for efficiency relating to power on the datasheet, but it also applies to energy. So the output energy is equal to 0.53, the efficiency, multiplied by the input energy of 1.85 times 10 to the 10 that we found here, giving an output energy of 9.82 times 10 to the 9 joules. Part C. It is suggested that this turbine could supply all the energy for an isolated group of houses. Explain why this is not a good idea and suggest an alternative. Well, the main problem with wind power is it is not reliable. When there's no wind, there's no electricity. However, the turbine could be backed up by a reliable system, such as an oil-burning generator, which could be used to top up when the wind power is not sufficient.